our astronomer, Rachel. How's it going, Rachel?
Good, yeah.
So
Doing
last
well.
night, last night we had a really fun cosmic night. Talked to Dr. Sean Brooks from JPL. Super cool conversation. Actually, lots of fun conversations that we had. Make sure to check out that. If you weren't with us last night, you can find it on our YouTube page. But we're going to follow up because we had so many great questions all about gassy giants, and we're just going to continue on with that theme because there's lots to talk about when it comes to these gassy giants. Where I was certainly inspired last night. So I don't know about you, Rachel. You seem to be really nerding out
I
with
really
that.
was, it's weird reading his white papers and going through his repository of papers and then actually seeing him and meeting him in person afterwards. So that doesn't happen to me very often. So that was
Yeah.
really cool, being able to ask him my burning questions.
Well, actually, that's a really interesting point you're bringing up, and maybe let's actually just start right there because you talked about a white paper. Maybe just like tell people out there what exactly a white paper is, because Dr. Brooks, obviously, he is a scientist. He works for JPL, and a white paper is a very specific kind of paper. It's not just a white sheet of paper. What exactly is a white paper?
So a white paper is a paper that highlights the salient questions for a particular mission or a particular field or subfield. And for this particular white paper, he was highlighting, and him and a few other authors were highlighting what the scientific objectives and the goals of the Europa Clipper mission were, and other missions going to explore the Jupiter and Saturn systems. And so I thought that was a great place to start, diving into all the science that Dr. Sean Brooks has going on. And yeah, it's an interesting paper. If you want to take a read, you can look it up very easily. I would highly recommend it.
Have you ever written a white paper?
No, but I hope that one day I will be able to at some point.
All right, so we're going to get into gas giants, and if you have any questions, please put them into the chat. And if you know why I have a T-Rex record right here, that's going to be a little spoiler. Maybe some of you know there's something associated with the theme this week. Maybe about that record, I'll let you know at the end if you don't already guess it. But let's get to your presentation, Rachel, all on the gassy giants.
For sure. All right, so I'm just going to share my screen here. So hopefully you should be able to see the lovely fisheye view from our planetarium software. And you should be able to see the planets going around the sun. Do you see that, Michael?
Sure do.
Awesome. All right, so in our solar system, astronomers often divide the planets into two families. We have the inner rocky terrestrial planets and the outer giant planets. But then there's this question of, well, why did astronomers group them this way? And what was responsible for this great divide? Well, to answer this, we do have to travel a little bit back in time to around 4.5 billion years ago when our solar system was first forming. And by looking at this formation evolution, we'll be able to see why the planets have the order and arrangement that they do today. Now, there is a widely accepted theory of planet formation, and it was actually jointly proposed by a geologist and astronomer. So it goes that the building blocks of planets, which we call planetesimals, were these little bits of orbiting material that condensed into clumps, and they got larger and larger as gravity clumped them together until they grew big enough for that gravity to form them into spheres. So planets and moons were built up this way, with the leftover debris floating around, forming comets and asteroids. Now, around 2 decades ago, chemists realized that these planetesimals had really different compositions depending on their distance from the sun. So we found that nearer to the sun or closer to the star, only rocky material could withstand that intense heat that you're getting from the sun. And so the first 4 planets are all small, solid, with that rocky material. Now, the planetesimals that ended up forming the outer Jovian planets contained higher concentrations of these substances, which they were called ices. And so they formed the outer giant planets. So that would be Uranus and Neptune as the ice giants, and Jupiter and Saturn as our gas giants. But now the question is, well, where do we draw the line for calling something a planet? And a good example of this is looking at ex-planet Pluto, which was once a planet, but then got demoted to the status of a dwarf planet. So let us jump there really quick. Here we go. And here's Pluto. Oop, and it's going a little bit too fast. Let's start slowing that down. Here we go. So Pluto was once considered a planet until new discoveries triggered some scientific debate on whether or how best to describe it. And the body that did this was the International Astronomical Union, or what we call IAU. And they're the same governing body that defines the 88 modern constellations that we have now and that help us map out the sky. And so their definition for a planet, which they came up with in 2006, had 3 specific criteria. The first is that it must orbit a star. So in our cosmic neighborhood, that would be the sun. The second is that it must be big enough to have enough gravity to force it into a spherical shape. And the fancy physics term for that is hydrostatic equilibrium. And the third condition is that it has to be big enough that its gravity has cleared the neighborhood around its orbit. Now, that last condition is actually the one that Pluto fails, unfortunately, because in all of its billion years of existence, it still hasn't managed to clear up its orbit, much like I still haven't managed to clean up my room. Now, it shares its orbital neighborhood with trans-Neptunian objects, like things called Plutinos. Alrighty, so after our solar system formed, Jupiter took most of that material left over after we formed the sun, and it ended up with around 2.5 times the combined mass of all the other bodies in the solar system. Now, for this reason, gas giants are often called failed stars because they contain the exact same basic elements that our sun has. So that would be hydrogen and helium gas, and they also have a little bit of other stuff, but they have all the same main ingredients that we would expect a star like our sun to have. And the term gas giant was from a science fiction writer in 1952, as most things in astronomy are named after science fiction concepts. And it originally referred to all the giant planets. But then now we actually move away from that to differentiating between the gas giants, so Jupiter and Saturn, and the ice giants, Uranus and Neptune. And Dr. Sean Brooks yesterday actually brought up a great point as to why this naming system and convention is important. And that tells us a little bit more information about when these planets formed and why and how they look the way they are today. And so he was talking about how these ice giants, Uranus and Neptune, are a little bit smaller, and Jupiter and Saturn are a little bit bigger. They formed a little bit earlier. And I thought that was a very cool point. Now, the bigger a planet becomes, the heavier the material is weighing down on its center. You probably experience this, this force or this pressure when you go underwater. So the deeper you go, the more water is above you in that column, and the more mass and stuff is pressing down on you. So you do feel a little bit more pressure the deeper you go underwater. And the same thing is happening in the cores of these giant planets here. So in the center, the tremendous pressures and temperatures cause these centers of Jupiter and Saturn to be hotter than actually the surface of the sun. It's incredibly hot, high pressures, high temperatures in the center. Now, if you travel deep into the atmosphere, this hydrogen gas is actually compressed into a liquid. And it's kind of a funny thing to think about that this actually gives Jupiter the award of the largest ocean in the solar system. And it's not an ocean of water, it's actually an ocean of hydrogen. Now, if we travel even deeper still, the pressure becomes so great that scientists think that electrons are actually squeezed off the hydrogen atoms by all this pressure. And it actually forms a electrically conducting state for this liquid. So it's almost like a metallic state that acts a lot like a metal. Now, of course, I can't talk about Jupiter without talking about its great red spot. With no solid grounds to weaken storms like we do have here on Earth, this giant storm has been raging on Jupiter's surface for many, many years. But astronomers have known for some time that it is getting a little smaller. It's shrinking in size. And if it keeps shrinking at its current rate, by 2040, we might just have to call it the Great Red Circle because it'll become a little bit more circular in shape. Now, there was a question yesterday about why is this red spot shrinking? And Dr. Sean Brooks had a great answer, which is we don't know. So like its fellow gas giant, we also have Saturn. Now, Saturn is also a ball of mostly hydrogen and helium, and it's actually the only planet in our solar system that has an average density less than that of water. So what that means is if we could build a bathtub big enough to hold Saturn, it would actually float. Now, as a gas giant, Saturn doesn't have a true surface, and the planet is mostly swirling gases and liquids deeper down. And at its center is a dense core of metals, things like iron and nickel, and it looks a lot like Jupiter's core, but is much smaller. Now, while a spacecraft wouldn't have anywhere to land, it wouldn't be able to fly through Saturn in one piece either. The extreme interior pressures and temperatures would melt and vaporize the spacecraft, much like it did in Cassini's final moments. Now, a cool feature on Saturn is that it has this weird hexagonal storm at the North Pole. And this pattern was first noticed by Voyager 1 and more closely observed later by Cassini. Now, it's really big, so it's around 30,000 kilometers across, and it has 320 kilometer per hour winds blowing at its surface, causing this massive rotating storm. Now, what's interesting is that scientists on Earth tried to replicate the storm and replicate the six-sided shape that it has. And they did this with liquid, and they tried spinning the liquid at different rates depending on the distance from the center. So they spun the fluid near the center a little bit differently at a different speed than they did with fluid at the periphery or at the edges. And they found that they were able to make shapes like a six-sided hexagon, but they also made shapes with 3 and 8 sides. And a really cool, I guess, a way to think about it that Dr. Brooks brought up yesterday was if you imagine a sinusoid with 6 humps and you kind of bent it around in a circle, then you would have the 6-sided shape, and it looks a lot like the Saturn hexagon. So that was an interesting way and a new way that I learned to think about why we get this hexagonal storm. Now, Saturn also has the greatest number of moons in our solar system. It has 82, and that actually surpasses the number that Jupiter has, which it has 79. And this recent development actually came with the discovery of 20 new moons last year, where astronomers went back and looked through legacy data, and they ended up finding a few more moon candidates. So even though Jupiter is the largest planet in our solar system, Saturn takes the crown for the greatest number of moons. And we do have a few missions dedicated to exploring some of Saturn's moons, in particular Titan and Europa, the latter of which Dr. Brooks was a part of. He's a part of the Europa Clipper mission. And I highly encourage you to go listen to our Cosmic Nights yesterday, because that was a really interesting perspective from an actual scientist working on these missions and seeing what that's like. Now, before I let you go to the Q&A period, I thought I would show you how to find Jupiter and Saturn in the night sky right now. So here I have Jupiter and Saturn, so you want to look towards the south, and we're lucky because they are still quite high in elevation and altitude on our nighttime sky, so you can still see it well above the treetops, and you want to go around that 10:30, 11 p.m. range to be able to see them. Jupiter will be this extremely bright point of light, and just a little bit to the left, you'll see Saturn lagging behind. And so I very much encourage you guys to go outside. I went outside 2 nights ago on a run, and I was looking at Jupiter and Saturn as I was running, and it was just a brilliant sight. Alrighty, so then I'll end right there, and if I can figure out how to stop sharing my screen, we will bring Michael back. Hello.
Yeah, absolutely. For anyone looking over to the south, you can't miss them. I think Jupiter actually right now is the brightest object besides the moon up there, brighter than any other star. So once you found that bright object, the next bright object right to the left, you've got those 2 gas giants with your very own eyes, which I think is really cool. So we've got lots of questions. We've actually got questions left over from last night. We also got questions that came into us from Instagram, which is another great way to interact with us. If you don't follow us on Instagram already, you should. We're going to introduce someone who's been running our Instagram account a little bit later on this program, but hit us up at Space Center YVR on Instagram and also Twitter as well. So let's start off. There's actually 2 questions we're going to combine here, because you did talk about the spacecraft's Cassini obviously went into Saturn at the end of its mission. So the first question that Jasmine had was, do we take any special consideration to preserve the environment of gas giants or their moons when we send probes to study them, especially when we're looking for life? So that's the first question from Jasmine. And then I think related to it is from Jillian. When we think about gas giants, they're full of gas. So theoretically, let's say if you had a strong enough spacecraft, could you just like go straight through this planet because it's just made of gas? So I've combined those 2 questions for you about sending spacecrafts through the gas giants.
So I'll start with that question of contamination and whether or not going to a planet or a moon or wherever it is we're going in the universe, really, whether or not we are bringing contaminants from Earth and introducing them into this brand new system. And, that is a major concern. And we actually see that concern happening here on Earth. Yesterday, I mentioned Lake Vostok, which is a subglacial lake in Antarctica, and they're doing ice core drilling to get ice core samples. And they're actually doing that to look at the climate record that's held in these ice cores. But there is that concern as when you're drilling down into this subglacial lake that hasn't, seen light in however many years, are you introducing something that could kill any life forms down there? So we have to be really, really careful whether or not we're introducing, the common cold to these space microbes that have never seen the common cold ever before. So we do take precautions and the necessary steps to protect and, try to avoid that contamination. And going on to
with the viruses.
I know. We'll never get away from it.
Well, it is good to think about, because perhaps humans, maybe we haven't thought about viruses more than just like the common cold, but now we're very, very vigilant. And now we know that even when we send spacecrafts, we have to be very careful with them.
Yeah, I think it's definitely a good way to think about cleaning contaminants as we're going and visiting in these other worlds. But I'll transition into Jillian's question, which is, if I had a super strong spacecraft that was almost indestructible, can I still fly through? And the answer is that deep within these gas giants, although we're not totally sure the interior structure of it, because it's very hard for us to get direct samples from the interiors of these gas giants, there is this idea that the matter in there exists in this, what I'm going to call a supercritical state. And that's a state of matter where it's not definitively in a liquid phase and it's not definitively in a gaseous phase. So it's somewhere in between, but it does still have a lot of resistance as you're trying to move your way through it. So if you had a perfectly indestructible spacecraft, then maybe, but it might still be a little bit hard to push through all that matter that's heavily and densely packed in the center.
Yeah, we certainly, we played a really cool video last night as well that was sort of theorizing what it might look like if a spacecraft had dipped down into those clouds. And boy, wouldn't that be a cool mission to design? Of course, you would have to design something really sturdy. But yeah, with the Juno mission, they discovered these really interesting storms that they've called mush balls. And Dr. Brooks talked a little bit about that. And we played this as an animation of what it might look like to go and study those storms that are called mush balls. So check that out on that video from last night. One of the questions, so again, sort of like talking about the cores of gas giants from Instagram, Parker asked, do the cores of the gas giants grow?
Oh, that's a good question. So as I mentioned, it's very hard for us to get samples from the core that are definitively from that core material. So we have these alternative techniques that we use to get around that. Things like using seismology, mineral physics, and things like planetary dynamics and combining all of these to try and understand the core when we can't directly do measurements, do in situ measurements. Mm-hmm. And a follow-up idea to that is that because Jupiter isn't actively accreting material, the pressure isn't going to change, because if you had, let's say Jupiter ate another planet and accreted it, got a little bit bigger, you'd have more material. It's the same idea of having more water above you, pressing down on you, you have more pressure, and your core radius would grow that way. But because Jupiter is kind of in a more stable configuration and more stable shape, it's not eating other planets, let's say, and so the core would stay around the same size it is now.
Although it does eat comets and occasionally asteroids.
It does. And that was such a cool question that I got to ask Dr. Brooks yesterday that I'm going to relay because I just think it's absolutely amazing. So I asked him about comet Shoemaker-Levy that crashed into Jupiter in 1994. So it broke apart in July of 1992 and then crashed in there July of 1994. And I was wondering if there was any lingering impacts or influence from that comet impact. And what was really cool is that he said that you could actually see the remnants of that comet crashing into and passing through the rings of Jupiter, which is kind of a weird thought, because you would think that, a long time has passed since then. There's a lot of debris floating around, and maybe something like shearing effects would get rid of that evidence or footprint that the comet was there. But he said that it's still there, and it's kind of a weird thing that it is still there, but I just thought that was an amazing little tidbit.
Yeah, it's like a cosmic accident. We have all of the evidence still.
Yeah, and it's almost like an interplanetary car crash almost.
Yeah.
I don't know.
Well, ICBC is going to have their hands full. Let's keep going with sort of like the core here. Another question from Keith, another really good question. So if the core of Jupiter and maybe other gas giants are hotter than the sun, why aren't they stars themselves?
Ooh, so the answer to that is, so even though Jupiter and Saturn are made out of the same material that the sun is, hydrogen and helium, uh, surprisingly, the answer is that Jupiter is just not big enough. You know, we can fit 1,300 Earths inside of it, but our sun is much, much bigger than that. I believe we can fit something like 1,000,000 Earths inside the volume of the sun. So it really needs more temperature and pressure that I've been talking about in the centers of Jupiter to be able to jumpstart that process of nuclear fusion, which gives our sun its energy and drives the sun. But it's just not big enough, and that's the answer.
Oh, it's always about like demotions. I mean, like nobody really talks about, Jupiter and Saturn being demoted from being a sun to a gas giant.
Yeah, there's no participation ribbons here.
I mean, I think everyone just needs to accept who they are. Jupiter, you're not a sun. You're just a gas giant.
There's a message in there somewhere.
Let's go to Pride, friend of the almost every week, who talks about hydrogen and helium. So our gas giants are made of these elements. So is most of the universe just hydrogen and helium?
Yes. So hydrogen and helium are the two most abundant elements in our universe because they were the two that were around when we first formed the universe. And we didn't get these other heavier metals, which when I say heavier metals, astronomers are really referring to anything that isn't hydrogen and helium. We didn't get these heavy metals until we started getting stars with that incredible, almost like a pressure cooker, being able to form these heavier and heavier elements. And with things like gold in your jewelry or iron in your blood, all of these heavier elements were formed in more energetic processes, things like supernova that had enough energy to fuse and form these heavier elements and then eventually eject them out into space where they land on places like Earth.
Yeah. Yeah. So like hydrogen and helium, they're everywhere. They're in us. They're floating around everywhere. Let's go to, actually, this is a really interesting question that we're going to go to. So you briefly touched on how Jupiter and Saturn are our gas giants. Now, when I went to school and I had my book and I would open up the gas giants, there was 4 gas giants, which included Uranus and Neptune. But once again, they have been sort of recategorized as ice giants. So we had a question actually from Simon talking about the storms. So if we see storms sort of like these mush balls on Jupiter, don't really see them that much on Saturn. So could we also compare those to Uranus and Neptune? Like, are the same types of storm systems happening? Like, are mush balls potentially happening on Uranus and Neptune?
So it depends on composition. So while these giant planets all have very similar compositions, the outer ice giants have things called ices. And what these ices are really referring to is this group of incredibly volatile materials. And when I say volatile, it means that the material likes to spend most of its time in a vapor state. And so when we have storms on Jupiter and Saturn, we get a little bit of a different effect. And there's actually a spot on Neptune as well that would be interesting to compare to the Great Red Spot on Jupiter. But things like mush balls come about because of high levels of ammonia. And I think lightning storms also play a part in mush balls. But so while they are quite similar, we do still have that differentiation between these volatile ices and the gas giants.
Yeah. And one of the things that our big question of the night last night, which we asked everyone, was where would you want to go next? Because we're going to Europa, we're going to Titan, we're going back to Mars. Where would you go? And Dr. Brooks was kind of torn, but he was certainly kind of set on certainly going to those ice giants, either Uranus or Neptune. Maybe put in the chat where you'd like to go next. But certainly Uranus and Neptune, even though we have beautiful pictures, they're pretty much all from that Voyager flyby in the 80s and also from Hubble Space Telescope. So we have not been close to those planets in a long time. So I think certainly those 2 ice giants are due for a visit. We are going to take a bit of a pause here because in the last 5 minutes, we want to introduce to you our summer students, mainly because I know that you're going to miss Rachel and I, but Rachel and I are taking vacation next week. So we're going to bring in our summer students who have been working with us on our Instagram, also creating the content on the blogs. Hopefully you've been going to our website. Every week we have a brand new blog. If you haven't caught up, read them. They're really interesting. And they have lots of links that you can go to for activities, for added information. So much cool stuff on there. As we've transitioned a lot of our programs online, they've really helped us out. And their big sort of summer project is for them to present to you 2 p.m. next Thursday. Jasmine and Justin are going to be talking about neutron stars. Really cool. Hi, Justin and Jasmine.
Hi.
Hello.
So neutron stars, how are you guys feeling about this? I know that almost everything else is gone out of your life and you're just thinking about these crazy objects deep in the universe. How are you feeling about neutron stars after you've delved into it, Jasmine?
Well, I've always kind of been a fan of neutron stars, but lately I've just sort of been like living and breathing neutron stars because I've been writing the blog and like making the playlist and putting together the presentation. So I've definitely learned a lot more about neutron stars. So I'm excited to share that with everyone next week.
Awesome. Yeah, I definitely check that out. And Jasmine, you've been developing, you said the playlist. So what exactly are the playlists that people can find on our website? What have you been putting on there?
Oh, so it's sort of, so if you go to our website and you find the blogs and you scroll all the way down to the bottom, there's these playlists. There's usually like a junior one and a senior one. So if like, depending on like how old you are, I guess. But we have like junior astronomers and senior astronomers, and you can sort of look through activities. I've sort of just been, I guess, surfing the web and putting together like interesting resources that I found, or like cool games you can play, or like things you can make to sort of like learn even more about the topic that the blog is about.
Awesome. Yeah. So we're going to be transitioning, of course, like as we go into fall. We may not always be here 2 p.m. on Thursday as we sort of shift into school gear. Everyone out there maybe is going to school. Maybe you're learning from home. Maybe you're actually going to school. There's going to be obviously lots of changes in our lives. Make sure to stay tuned to our website. Make sure to stay tuned to our social media. And speaking of our social media, Justin, you've been doing some great work on our Instagram. How have you found working on the Instagram tool this summer?
Absolutely. No, it's been great. I think I was just doing a tally, and I think we've put up around almost like 250 different unique Instagram stories over the past couple months since I've been here. And it's been so much fun. And for those of you out there that have been commenting on our Instagram stories, it's been great. Those of you that have been asking questions that I can relay back to Rachel and Michael as well. I've been doing a ton of that as well, making sure that I can kind of support the voice of the Space Center. But it's been so much fun hearing from all of you online as well.
Yeah, absolutely. So that's obviously a great resource. If you have a burning question, going to Instagram is a great way to connect to us, and also a great way for you to share with your friends and family about all the work that we've been doing over the course of the summer. So Justin and Jasmine, good luck next week to everyone out there. Please join them. Be nice to them. Your substitute teachers, I know how things go when you have a substitute teacher. You like to maybe play pranks on them. So no pranks on Justin or Jasmine. Be nice to them. But they're going to do great. Jasmine did a practice run this afternoon, and Rachel and I really loved it. So for Rachel, we're going to take a bit of a break. But for everyone out there, thank you so much for supporting us through the summer. We will be back with so many cool events coming up at the Space Center. If you haven't checked out our website, we have some in-person events coming up. We have an event all about robots coming up. If you've got some family members that really want to learn about how robots work, we're going to be using these really cool tools called Ozobots. If you've not used Ozobots, they're really cool. You can program them, and they kind of give you an introduction to how we potentially use robots on other worlds. That's going to be actually an in-person, physically distanced workshop that we're going to be doing at the Space Center, so make sure to sign up for that. And then as we get into next month, we're going to be delving into the theme of exoplanets. So we're going to have a cosmic night on exoplanets. We're also going to have a workshop that you can develop what you believe might be an extremophile living on potentially one of these exoplanets. This is a classic workshop that we do for kids in school, but you can come with your family, also in person, physically distant at the Space Center. So we do got some plans, so things are in the works. Thank you so much for supporting us. If you would like to support us more and you'd like to donate, you can go to our website, go to the donate now. We really appreciate it. Justin and Jasmine, have so much fun. Rachel, I will see you in a couple weeks when we're off vacation.